All right, so as I promised in the last class, we will be doing some examples today. Um, so the first example is, from the kinematics, where we're trying to find out acceleration if velocity were given in the Eulerian coordinate system. So, so here's that example. So suppose that the velocity is given in Eulerian framework. So it's the function of small x, spatial coordinate and time, and it is given equal to, okay, somebody has his mic on. Please unmute your mic, mute your mic, yes. Yeah, now it is good. Okay, so this is the velocity profile. Okay, plus 2u a square x1 x2 over x1 square plus x2 square, and that's in e2 direction, plus ve3. All right, so u a, then this v, these are constants. Okay, okay, so given this velocity profile, can we find out what will be the acceleration? Okay, just give me 10 seconds. I'm just coming back. I think there is a noise coming. Okay, sorry for the interruption. So we have to find out acceleration in the Eulerian framework. Velocity is given here, and you can recall the formula. So it is not straightforward. It is equal to del V over del T at constant small x plus gradient of V into V itself, isn't it? So you just have to apply this formula. But before applying this formula, can we try to understand the physics of this motion? So what do you think? It looks like quite complicated. First of all, will there be some acceleration just by looking at the formula? What do you think? Will it have some acceleration? Does it look like there will be an acceleration?
Sir, it does not look, because it does not involve any function of time, but because of the gradient of v, because of del v term, so that acceleration will be there.
So you're saying that there is no acceleration?
I mean to say, sir, there is acceleration.
Yes. Okay. But you see that the formula of velocity has no time dependence. There's no time present explicitly in the formula. So if you go to any spatial coordinate, any spatial location, the velocity at that location is independent of time. That's what this formula says. You go to a location small x1, x2, x3, and at that point, velocity is not changing. So Does it mean that acceleration is zero?
We'll just have the convective acceleration term.
Exactly. So it will convective acceleration. So it's not zero because when I fix a small x1, a small x2, a small x3, I'm not fixing the particle. Whatever particle comes to this point, it will always have the same velocity once it reaches this point. But at different time, we have different particle at this location. So therefore, just because velocity is not a function of time in this Eulerian framework, it doesn't mean that acceleration is zero. And this is also called, in fluid mechanics, because as I told you, Eulerian framework is mostly used in fluid mechanics. So they also say it is steady state flow. Steady flow. That means flow is not changing with time, it is fixed in space. Okay. Now, having seen this, maybe let us also try to find out what is the physics, or what kind of flow is this. So you see, in the Cartesian coordinate system that has been prescribed here, the formula is quite complicated, but maybe we can try to use cylindrical coordinate system. Okay, so let us say we substitute x1 equal to little r cos theta, and y1 is x is just x, not x1. So x equal to r cos theta and y equal to r sin theta. So what happens to velocity then? So it becomes u into a square and x1 square. So we have a small r square common into cos square theta minus sine square theta, right? Divided by little r to the power 4. Okay, so as per the question, this is x1 and this is x2. So this is in E1 direction plus 2u. So that is 2u a square into little r square divided by little r to the power 4 into sine theta cos theta, right? And this is E2 plus big V into E3. Okay, now we have to use some trigonometric identity. So that means small v is u a square by r square into cos square theta minus sine square theta is cos 2 theta into E1 plus u a square by r square into sine 2 theta into E2 plus big V into E3. Okay, and can we also change E1, E2 to cylindrical coordinate systems ER and theta? So I hope you guys are aware of cylindrical coordinate system. So if cylindrical coordinate system is there, then at any location little r theta, ER is pointing radially outward, whereas E theta is perpendicular to ER and in the direction of increasing theta. But E1, E2 is always the same. Okay, so all right, so let us try to write down E1, E2 in terms of ER, E theta. So E1 becomes ER cos theta minus E theta sin theta, whereas E2, that's well, it is cos theta E theta plus sin theta ER. Are you with me? I hope you can see it. You just have to resolve E1 and E2 along ER and E theta. Okay, let's get back. So this becomes U A square by R square, and E1, that means it is cos 2 theta into cos theta, and then you have ER, and another one will come from here. So okay, this is ER, and that's sine 2 theta sine theta plus sine 2 theta sine theta. And then the E theta component is minus cos 2 theta sine theta plus sine 2 theta cos theta into E theta. And finally, it is V into E3, which is same as EZ for cylindrical coordinate system. Okay, and then this becomes, well, you can see within the bracket, the first bracket, that's cos 3 theta, cos A cos B plus sin A sin B. No, sorry. So that's cos theta actually. I'm sorry. So this is U A square by R square cos theta ER, and the next one is that's sine 2 theta cos theta minus sine theta cos theta. So that's sine theta. Okay, and plus VEZ. So that's the velocity profile. I hope I have gotten it correctly. Um, are you guys okay with me? Have I made some mistake?
It's fine.
It's fine, okay. So this is V as a function of x. So this looks easier now. And if I try to draw the velocity profile in r theta coordinate system, how does it look like? First of all, look at the magnitude. What is the magnitude of this velocity? So the magnitude of velocity, you take the square of each of the coefficients and then take the square root, right? So that is simply u a square by little r square. So that's the magnitude square of velocity. So it is constant. So at any point, this velocity is constant. And can you see in what direction is this pointing? What do you think? In what direction is this pointing? So if I try to further write this, it looks like it is u a square over r square into cos theta er plus sine theta e theta plus big V E Z. So try to understand the first term here, this one. what is this direction within the bracket? Cos theta er plus sine theta e theta. So let us try to understand that. So I go to a point r theta, and here is your er and e theta, okay, which is making an angle theta from here. So which direction is this? Cos theta er plus sine theta e theta. Which direction is this? So I guess that is this direction. So this is at an angle theta, of course. So that's cos theta er plus sine theta d theta. Okay, so what this tells us is that velocity at any point r theta, it has got its z component is fixed, it is coming out, but the in plane component, that is making an angle of theta from the radial direction, and it's constant. Okay, so the in plane component makes an angle of theta from the radial direction, and it's constant. So again, if I try to draw its velocity profile, so at any point when I'm here, it's pointing outward like this. When I'm over here, it's going like this. When I'm over here, it's like this. Then when I come over here, it will come inside, I guess, because the theta, so it has to be theta, no? So as you go in this direction, theta is increasing. So the angle from radial, that will also increase. So here, for example, theta is 90 degrees. So angle from radial direction is also 90 degrees. So that's the direction of the velocity. So it starts with radially outward, and as it goes here, then it comes inside also. Okay, so for some part it is going out, and for the other part it is going inside, and then it also has a z component, so it is also coming out plane. All right, so that's how the velocity profile is. And let us see what is its gradient for divergence, for example. What is the divergence of the velocity? So in cylindrical coordinate system, if you want to get the divergence, then we have to do del v over del r dot with er plus 1 over r del v over del theta dot with e theta plus del v over del z dot with ez. Okay, that's the divergence in cylindrical coordinate system. So now this velocity we have to express in er, e theta, ez. Let me write it down more clearly. So this is del by del r of vr er plus v theta e theta plus vz ez. Okay, and this has to be dotted with er plus next one by r del by del theta of vr er plus v theta e theta plus vz ez, and this is dotted with e theta. Okay, this is the definition of divergence that we have learned. Please ask me if you are not following. And then the last one, del by del z vr er plus v theta e theta plus vz ez. and finally it is dotted with Ez. Now you see the problem here is that we can't take the basis just outside because the basis vectors Er, E theta, Ez are also changing. But the change is such that Er, E theta, Ez, they are independent of R. Look at this picture for example. You move from here radially outward. Er always points in the same direction. So as you change your location along the radial line, Er and E theta do not change. But if you change theta, then Er and E theta change. Okay, and in fact, you can show that del Er by del theta, that's going to be equal to E theta. And likewise, del E theta by del theta, that's going to be equal to minus Er. Please don't worry if you don't know how, if you have not seen this before. Because our goal here is not to derive them, we just want to see what is the divergence. But deriving this is also not difficult. So coming back here, so you see when we have del by del r, then Er, E theta, Ez, they do not change. So you simply have to take the derivative of the coefficients and further you have to dot with Er. So only this term is going to survive and you have del Vr over del r. Then come to the next one, and here you see you have to dot with E theta. Of course, one will be that. Okay, before that, you see you are taking a derivative with theta. So Er and E theta also have to be taken the derivative. So what you will have here is 1 by r del Vr by del theta into Er plus Vr del Er by del theta plus del V theta by del theta E theta. Okay, I have to make some boundary plus V theta del E theta by del theta, and then it has to be dotted with E theta. Okay, and so what is this going to give me? This thing over here, that's 1 by r del Vr by del theta Er plus Vr into del Er by del theta, that's E theta, plus del V theta by del theta into E theta minus V theta into Er, and then I dot with E theta. So when you dot, this one goes away and this one also goes away. So what you have finally is, so from here you get just Vr by R, and the next one is 1 by R del V theta by del theta. Okay, and finally from the z derivative from this one, you will only have del Vz by del z. So the divergence in cylindrical coordinate system is then del Vr by del r plus 1 over r del V theta by del theta plus Vr by r, and then you have plus del Vz by del z. Okay, and now you have to plug in the formula Vr V theta Vz. So look at the formula of Vr V theta Vz. So that's your Vr, and this is your V theta, and this is your Vz. So del Vz by del is 0 because V is constant, capital V. Then coming to del V theta, when you do del V theta by del theta, the sine theta becomes equal to cos theta. Okay? And then likewise you have to do del Vr by del R. So let us see what you get. So del Vr by del R, so this is, if you recall, it was UA square by R square. So this becomes minus UA square by R cube into cos theta plus 1 by R del V theta by del theta, which is plus 1 by R into UA square by R square, and this becomes cos theta, I guess. Yes, this becomes cos theta. And then you have one more term, VR by R. And what is VR by R? That's UA square by R cube into cos theta. Am I correct? And finally, you have 0. Oh, sorry, you'll have 2 also here because it was UA square by R square, no? So when you take the derivative, you get minus half. Okay, and then finally you see that all of them cancel. So divergence of velocity is 0 here. And you know what kind of flow is this? If divergence is 0 of velocity, it's called incompressible flow. Now the final thing is the acceleration. So acceleration we know is del V by del T plus grad V into V, right? And this is 0 here. So we have to find out gradient of V. Now taking the gradient in cylindrical coordinate system is again not easy for the same reason that you just saw that when you took the divergence, you got an extra term. Do you see that? You got this extra term in divergence. If it were divergence in the Cartesian coordinate system, you would only have this, this, and this. But here you have an extra term. But the advantage is that you are not taking derivative with respect to r and theta, and the formula is very simple in terms of r and theta. But it was very complicated in x1, x2, x3. Now to obtain acceleration level, you see that I have to get gradient of velocity. Okay. So how do I get the gradient? So just like divergence, you have to apply the formula of gradient. So that is del by del r
Hello, sir.
v. Yes,
Sir, I had a doubt in the expression that you wrote for del dot V.
yes. Tell me
Uh, can you please scroll up? Um,
even more.
yes, just a bit more. Yes, sir. In the expression, like del by del R of VR ER plus V theta E theta plus VZ EZ dot ER, like
Yes.
that, the first term, we are
Yeah.
expanding. In that view, got only del by del R of VR, right? Only
Yes.
that, on one more term is not there, like V theta.
Which
With,
one, for example? Tell me. You see, when you take the derivative with respect to r, then er and e theta and ez, none of them change. The basis vectors change only if theta changes, not due to change in r or z. So therefore, here er, e theta, ez acted like a constant, and so you have to take the derivative only of vr, v theta, vz. But finally you are dotting with er, so only the first term survives. And that's what you wrote here. Is that okay? So the gradient is then plus del by del theta, and then you have 1 by r also. Why 1 by r is there? Because the gradient is with respect to space, spatial dimension, length dimension. So I have to I have to multiply with 1 by r therefore, because you see theta is dimensionless, no? That's why. And then v, and you have tensor product e theta plus del by del z of e tensor product Ez. Okay, so what is this going to give me now? So the first one, so now you have a lot of terms actually. So this is going to give me, so again, when you take derivative with respect to r, the basis vectors act like a constant. So you have del Vr by del r Er plus del V theta by del r E theta plus del V z by del r Ez, tensor product Er. Okay, then the next one, so that is going to have a lot of terms, plus by r, then del v by del theta. So the first is Vr Er, so this gives you del Vr by del theta Er plus Vr into del Er by del theta, which is E theta. Then V theta E theta, you have del V theta by del theta E theta minus V theta Er, and then del Vz by del theta Ez, and I have to do tensor product with E theta. Okay, and then the last one, this is easy again because basis vectors we don't have to take the derivative. So this is del Vr by del Z Er plus del V theta by del Z E theta plus del Vz by del Z Ez, tensor product Ez. Are you guys with me? So this is the gradient. If I want to write it in a matrix form, what will I get? So in the matrix, the 1 entry is for ER tensor product ER, and that's just this term here. So you have del VR by del R. In the 1, 2, you have to see all ER tensor product E theta. So where are ER tensor product E theta? So second one is tensor product E theta, so it has to be here. So you have 2 of them, you can see you have 2 of them. So you get 1 by R del VR by del theta minus V theta. Then ER tensor product EZ, that's here. So this is del VR by del Z. Okay, then you come here, this is E theta tensor product ER. So that's just one of these, which is del V theta by del R. Then E theta tensor product E theta, so it has also got 2 of them, and it is 1 by R del V theta by del theta plus VR. Then you have E theta tensor product Ez, which is very simple, del V theta by del Z. Finally, del, so this is Ez tensor product Er here, and that's del Vz by del r, and then Ez tensor product E theta, that's del Vz by del theta, and Ez tensor product Ez, that's del Vz by del Z. Okay, so this is the gradient matrix, velocity gradient matrix. And I have to multiply this with velocity itself, which is Vr, V theta, Vz. Okay? And this will then give you acceleration in cylindrical coordinate system, that's Ar, A theta, and Az.
So
Okay?
this is then like
So
writing
you
the
simply have to, yeah, please
Jacobian
say again.
that sir, this is then like writing the Jacobian, the gradient.
Well, yeah, it's like Jacobian, but you can see there are extra terms here.
Yes.
So you see, don't think of you have to get the Jacobian. You just see you have to apply the formula of gradient, and then once you have the gradient in tensor form, try to write it in the matrix form. That's it.
Okay, sir.
Can you see from here what is Az? So for Az, what you have to do is take the third row of this gradient and multiply this with velocity. Now third row of gradient, all of them are 0. Right? These are all 0 because Vz was constant. So therefore Az is also 0. Okay, quite simple. But for the other ones, you just have to put the formula and find out. All right. In fact, these are also 0. Anyway, so then I leave it to you to complete this. Okay, so this was about Eulerian motion, how to get acceleration. Now you can recall we also learned the kinematics of deformation, where we had a body in the reference configuration and then it was deforming. Deformation map F, and we presented a very general picture. So let us see some of the simple deformation maps. So number one is what is called uniaxial extension. Okay, uniaxial extension. Tensile testing. It is uniaxial extension. So it is like if you have a bar, you are stretching in one direction, but in the other direction, you don't let it stretch or compress. You are just stretching in one direction. And let us suppose this is E1 and I stretch by lambda. Okay. So what do you think? Can we try to write down the formula first of all? So small x1, I could say this is same as lambda times capital X1. And then small x2 is same as capital X2, and small x3 is same as capital X3. So this is the example of uniaxial stretching or extension. Okay. Now try to find out the deformation gradient matrix. Can you see how does it look like? So this is going to look like lambda 1 1 0 0 0 0 0 0. Do you agree with me? You see, this is your F1, this is your F2, and this is your 3. So you have to do del F1 by del X1, which is lambda, del f1 by del x2 is 0, del f1 by del x3 is 0. So likewise, you can find all of them. I hope that it is okay with you. Okay, and you see, you could also write this as the same thing. You can write as 1 1 1 0 0 0 0 0 0 identity matrix basically, plus this thing lambda minus 1 0 0 0 0 0 0 0 0. Okay, so this is the matrix form, and you can get back to the tensor notation. If you try to go back to the tensor notation, you will get big F is equal to identity tensor plus the tensor corresponding to this matrix. And you see what is the tensor of this matrix? You see it has only one non-zero. So it is E1 tensor product E1. So that's lambda minus 1 E1 tensor product E1. Okay, so this is the general form for uniaxial stretching. In fact, if the stretching is along some direction, let's say M, then you can say your capital F would then be identity plus lambda minus 1 into capital M tensor product capital M. So this is the general deformation gradient for uniaxial stretching. Along M. Is that okay with all of you? Anybody not able to follow? As I told you, you can interrupt me. Now, second one is called simple shear. Okay. Now, this is, I think I had also did it, I had done it in the last class perhaps, but I'll do it again. So, suppose this is E1, this is E2 and E3, and you have a body in the reference configuration. And after deformation, it becomes like this. So this is after deformation. All right. And say that this angle is alpha. Then what can you say about little x1? You see little x1, there is a drift. The body, the x1 coordinate of the body is not the same before and after deformation. So this is the displacement. So small x1 will be equal to capital X1 plus this thing. And you can see if this is alpha, then this is going to be this distance into 10 alpha, right? And that distance is x2. So this is x2 into 10 alpha. And small x2 will be same as capital X2, and likewise small x3 will be same as capital X3. Now if you try to find out the deformation gradient matrix, so this is going to be 1 1 1 0 0 0 0 0, and here you have 10 alpha. Okay, and you can get back to tensor form, and you can say that F is equal to identity plus 10 alpha into E1 tensor product E2. And what are the meaning of E1 and E2 here? You see, E1 is the direction of shearing. and E2 is the normal to planes which are being sheared. See, I can also relate this with this picture over here. Look at this picture. So E2, as I told you, is the direction in which there is shearing. And think of these planes. So one plane, for example, this is the plane in E1, E3. Then you have another plane here. You have another plane over here. So these are all planes having normal along E2, isn't it? And you see, it is these planes which are undergoing shear. Okay, I can make it a bit more nice picture. Let me make a nice picture. So I'll start from the top. So you will have this one. Can you see these planes? So these planes, you have three planes here which are having normals along E2. And these planes have shifted along E1 direction. So they are undergoing relative shearing, these planes. So therefore we say this is shear, and it is being physically visualized as shearing of parallel planes. See, all these three planes are parallel, having normal along E2, and they are undergoing relative shearing along E1. Okay, and this is the deformation gradient formula. And for a general shearing, then your F will be identity plus the tan alpha into M. Well, I'll make it big M tensor product big N, where big M is the direction of shear. You see, this need not be along E1, E2, E3. And big N is the normal to parallel planes which are being sheared. And the condition is that big M has to be perpendicular to big N. Okay, so this is the example of shearing. Can we try to find out what is the C? What will be C for this? Can you recall that right Cauchy green tensor C? So what is the C matrix in this case? So C, as you can recall, is F transpose into F. So for the above case here, What is F transpose F? So this is going to be 1, 0, 0, 10 alpha because it is F transpose, and it is 1, 0, 0, 0, 1 into F. 1, 10 alpha, 0, 0, 1, 0, 0, 0, 1. Okay, and then what is this? So when you multiply first row, third column, you get 0. Row, first column, you get 10 alpha. Second row, second column, you get 1 plus the square alpha. Then second row, third column, you get 0. First column 0, third row, second column 0, third row, third column 1. Okay, that's your C matrix. And from C matrix, can you see what is stretching along E1, E2, E3? What do you see? What can you say about the stretching of line elements along E1, E2, and E3? So lambda for E1, isn't that square root of C11? Because you can recall the formula, it is C E1 dot with E1. That's lambda. And this comes out to be 1. Likewise, lambda 3 is also 1 here. And lambda 2 is 1 plus 10 square alpha. And this is also perfectly fine. You look at a picture, look at this picture here. What is lambda 2? Lambda 2 is an element along E2 direction. Maybe I'll make that picture again. So here is the coordinate system. Well, it also gets a square root of sine. Sorry. So this is the original reference configuration, and after deformation, that's the deformed configuration. Okay. Now you see what is the length of this line element. So this is the E2 element, right? This is E2 element because it has to be directed along E2. So what is its length after deformation? This is the length. What is its value? Can you see? So if this is alpha, then this is sec alpha, isn't it? Assuming that this is 1, then this becomes sec alpha. So how much is the stretching? That's sec alpha. So lambda is sec alpha. Final length by initial length is sec alpha. And you can also see from here it is sec alpha. Okay, but the lengths, line elements along E1 and E3, they do not undergo any change in length. Similarly, you can notice the angle. Look at the line element along E2 and one along E1. What is the angle between them? That's 90 minus alpha, right? And can you recall that formula, cos of that formula? What was the formula for the deformed angle? So cos theta, that was, can someone tell me what was the formula? So if I'm not wrong, it is c time dot n divided by lambda m into lambda n. Is that correct?
Yes, sir.
Okay, thank you. So now take m equal to e1 and n equal to e2. Okay, and see, so above you get c12 divided by lambda 1 into lambda 2. And c12 is 10 alpha, and that's you divide by lambda 1 is 1 and lambda 2 is sec alpha, and this is simply equal to sine alpha, right? So cos theta is equal to sine alpha, which is cos of 90 minus alpha, and this implies theta is equal to 90 minus alpha, as it is in the picture also. Okay, so you can see everything is making perfect sense. Okay, what about the volumetric strain, for example, epsilon v? What is that equal to? So this, we know it is equal to determinant of f minus 1. Now what's the determinant of this matrix? You have to look at f. So this is f. What is the determinant of this matrix? How much is this? It is 1 itself. The determinant is 1 itself. And therefore epsilon v is 0. Okay, so in this case, the volumetric strain is 0 everywhere. So therefore, we also say it is a case of isochoric transformation. So you have a new terminology, isochoric deformation. So this is the deformation for which determinant of f is equal to 1 everywhere. So no volume change even locally. You take any small volume element in the body, anywhere, its volume is not changing. So it behaves as if it's an incompressible material. Okay? You see, it is important that it should not change at any point in the body. Not the full volume of the body, but at any point in the body. The volume change should be 0. Then we call it isochoric deformation. Alright, I hope you guys are with me.
Sir,
Okay, next. Yeah.
so how are we getting the determinant of deformation gradient as 1? That I could.
Okay, look at this matrix here. This is the F matrix, no?
Yes, sir.
Right? Just try to find out the determinant.
Okay.
How will you get the determinant? You will, let us say you expand it in the first row.
Yes, sir.
Okay, so you get 1 into 1 into 1 minus 0 into 0.
1.
I mean, you do it and you will get it is 1.
Yes, sir. Yes, sir.
Okay, and in fact, there is a nice formula. If you have lower triangular or upper triangular matrix, then the determinant is simply the product of the diagonal. And in this case, you can see that it is an upper triangular matrix. So determinant is going to be product of the diagonals, which will give you 1.
Okay, sir.
Okay, so now we'll talk of called rigid motion. What will be the deformation gradient for rigid motion?
Excuse me, sir.
Yes.
Sir, say something about the
Yeah,
normal to the area transformation?
yeah, yeah. Oh, you want to know something about that?
Yes, sir. So how the normal to the area is changing, because I see that normal is E2 and which is not changing. So, but if we
Exactly.
apply the formula,
Yeah,
then it is
that's a
F
very
inverse transposure.
okay, very good. Let us try to see that. Okay, I think that's a very good question. Let me apply that formula. So I just postpone this. So what about deformed normal? So can you recall the formula that normal n, deformed normal, is equal to F inverse transpose into undeformed normal divided by magnitude of this, isn't it? This is the formula for the normal. And at least in this particular case, we can see from the picture that the planes whose normals are along E2, it remains E2 even after deformation, right? So if we take capital N equal to E2, then small n will also come out, should come out to be E2. And let us see, is it coming out or not? So first of all, we have to find out F inverse. So F is equal to this identity plus 10 alpha, and what did I write there? Was it M tensor product N? Well, I wrote E1 tensor product E2, or I could also say M tensor product N. So what will be F inverse? Can I say that? Can I say that this will be equal to identity plus 1 by 10 alpha of n tensor product M? Let's just see. Is this to be the case? If it is the case, then F inverse into F should be identity, right? We know that this into this has to be identity. So let's check this. So identity plus, see, I'm just seeing, it may not be the case, plus n tensor product M into identity plus 10 alpha of M tensor product N. Now, when I work this out, I get identity plus identity into this number, which is 10 alpha M tensor product N, and then this number. So yeah, it is not the case. Maybe I think it is even simpler than that. I think this would be identity minus 10 alpha to M tensor, identity minus alpha of M tensor product N, and so I get here identity minus 10 alpha M tensor product N, and then you have plus 10 alpha of M tensor product N, and the last one is with a minus sign, of course, minus 10 square alpha of M tensor product N, but then you also have a M dot N, but M and N are perpendicular, so this goes away, and these two cancel each other. So this turns out to be identity. So we have found out the formula for F inverse. Okay, so F inverse is this number here, this thing over here. So this turns out to be correct, which means F inverse transpose is simply identity minus 10 alpha of n tensor product M. Okay, so now, so what will be then this thing over here. So small n is then F inverse transpose into capital N, right? And let us see what is this. And of course, I have to divide also by magnitude. So F inverse transpose into capital N. So I'll just write here identity minus 10 alpha n tensor product M into N and divide by magnitude. So in the numerator, then I'll have capital N itself. And then you see the second one, M dot N, it becomes 0, right? So this is N by magnitude, which is N itself. So you can see that small n is same as capital N, right?
Yes,
So
sir.
you see, formula is also telling you that the normal is not changing.
Yes, sir.
Okay, so this is a verification. All right. Any more question?
Sir, this way of finding F inverse,
Yeah.
the tensor of F inverse is just for the particular case like this.
Yes,
So
yes,
we
of
have,
course. It is a particular case. You can't do it for the general case. See, I was knowing that it has some simple formula, so I was trying this. But for a general, we can't have a analytical formula for inverse.
yes. Okay.
Okay. So, well, so today's class is more or less like a tutorial. So you can ask me more questions. So now I'll talk about rigid body motion. So rigid body motion means the body is simply rigidly translating and rotating without undergoing any change in shape or size, or no local strain generates in the body. Okay, so that's rigid body motion. So it is just undergoing translation and rotation. So suppose that if this is the reference configuration, okay, so the body could be undergoing rotation about some point, let us say capital X naught, okay, and about some axis also. So then it will simply, first what it is going to do is it's first going to rotate. See the same shape, it's just rotating. And if there is an extra translation also, then it could also translate. So this, so whenever such a thing happens, well, it doesn't look like it's about x naught. Maybe I think it could be somewhere. So if this is the point, then that's the point. Then I think it is somewhere over here. That point is somewhere here. And why I said this is because if it is rotating about x naught, then every point, the relative position vector of a point in the body related to x naught, that distance will not change, that its distance will not change. The direction will change, but the distance will be the same. Okay, so what I mean to say is if this is, let's say, capital X and this is capital Y, this is small x, this is small y, then small x minus capital X naught, its magnitude will be same as capital X minus capital X naught. And this holds for all capital X in the body. So this is rotation, and rotation can be realized through what is called rotation tensor. I think we also talked about this, no? Rotation tensor. So, yeah, I think we talked about this. And if it is rotating about capital X naught, then we can say that small x will be equal to that rotation tensor big R, which will which can be a function of time but not a function of capital X, because the rotation is same for every point in the body. Then only called rigid rotation, into capital X minus capital X naught, because it is rotating about X naught, and plus capital X naught. You see why I did so? Because first of all, you see, if you say capital X is X naught itself, then you will see that small x will be equal to X naught, and that should be the case also, because it is rotating about X naught. Okay, so anyway, this is the formula for rigid rotation of a body. Okay, and if there is some extra translation also happening, then you could also add the translation vector. So plus some translation vector t, which could be a function of time. So this is rotation tensor, and this is translation vector. And notice that both rotation and translation vector are independent of capital X. If it depends on capital X, then for different points in the body, they will be rotating or translating differently, and then it's not a rigid motion. Okay? Now, can we try to find out what will be the deformation gradient for this particular case? Maybe let us write down the component form of this formula. So small xi, what do you think, what is this equal to? Will it be capital R I J into capital Xj minus X naught J plus X naught I plus T I? Would you agree with this? I am just taking the ith component. Okay. Now, if this is the case, then what is del small xi by del capital Xj? Now you see Rij is independent of capital X, so it acts like a constant. Well, so I can't take derivative with respect to j, because j is already there, so make it k. And then I get del xj over del xk minus del x naught j over del xk plus del x naught I over del xk plus del ti over del xk. Okay, all right. Now what can you say about this term here? What is this? Del ti over del xk, what is it equal to?
Grad T.
Grad t. But you see that t is not a function of xk. T is, this big T is only a function of time, right? You see from here.
Okay.
It does not depend on capital X. So what is this going to be?
0 then.
0. Yes. Now, what about this one? What is this equal to? Anybody else?
Delta
What is
IT.
it? Roshan, can you tell me?
Sir, del ik.
Delta IK?
Yes, sir.
Del,
Okay. Okay. And anybody disagreeing with this?
Yes, sir. It should be 0.
Why?
because it is constant.
It is a constant, sir, right? X0 point, which is repeating, so it must be 0.
Yes, so both Niranjana and Rajnish, they are right. X naught is constant. Look at the picture. It is rotating about X naught. So X naught is not changing when you change the particle of the body. So therefore, this derivative is 0. Okay. Likewise, what can you say about this?
This is also 0.
This is also 0. And what about this?
Del jk.
Del JK, sir.
Yes, this is delta J. So finally, you have del little xi over del capital Xk, that's equal to Rik. And you can come back to tensor form and it says your deformation gradient tensor big F is simply big R, the rotation. So for rigid motion, deformation gradient is just a function of time. It's uniform in space but changes with time. All right? Now, if this is the case, what can you say about C, the right green tensor C? So C is then R trans into R, right? Because it is F transpose F. So what will this be equal to?
I, sir.
I.
I, right. So what can you say about stretching? What about lambda M? So that's C into M dot with M. What is this equal to? Vinayak?
So,
So 1.
1, right. You can see. So none of the line elements are undergoing stretching. Similarly, what about change in the angle, cos theta? That's C m dot n divided by lambda m into lambda n. And if m and n are perpendicular, what's then? So Cm is same as m dot with n divided by lambda m into lambda n. But because m and n are perpendicular, this becomes 0. So that means theta is equal to 90 degrees. So initial perpendicular, if they are perpendicular initially, it remains perpendicular. And that's the, I mean, shouldn't that be the case for rigid motion? If it's a rigid motion, then the line elements cannot undergo change in their length, nor the angle between them can change. Similarly, when you find out the strain, volumetric strain, that's determinant of F, so determinant of R, so that's also equal to 1, right? And that's again the trademark of this rigid motion. Okay. So that's about rigid motion here. There are several more nice examples in that book by Rohan Aberatne. I couldn't do more. I haven't done anything at all. There are so many nice problems. Look at chapter 2 and chapter 3. Well, we haven't finished chapter 3 yet, but you can look at chapter 2 and chapter 3, and there are several good examples. And when I give you questions, it will be from them, so you should really revise it. But it won't be the same, so that you are not able to copy it, of course. It will be similar. Okay, any more? So I'm done for today. I hope this session was a bit helpful for all of you.